So this is I'll just recall you that Stokes equation, right? Today, everything is based on this equation, right? Stokes equation. That is F equals 6 pi eta V. So this is a Stokes equation. From the Stokes equation, if an object moves at velocity V through a medium, this could be air, this could be water. So this is like a small spherical object, right? It should be small. And the radius of is A, and the viscous coefficient of the medium is eta. We know that from the medium on this object, it causes a resistive force or viscous force to the opposite side. So this viscous force can be gained using this equation, right? 6 pi A eta V. So that is what we talked last theory part, right? Okay. Then write down write down the subtopic motion of a, write down motion of a small solid sphere, motion of a small solid sphere falling through a liquid. Motion of a solid sphere falling through a liquid. Okay. So this is about like this, right? Let's say, so this is a liquid, right? And this object is falling, means immersing into the liquid, right? It is sinking actually. Let's say the radius of the object is simple A. So what are the forces acting on this? We have to describe the motion of this object, right? To describe that, we have to know the forces acting on this object. So obviously one force is mg, its weight. And if it is immersed in the liquid, there is a upthrust, right? Upthrust also is acting. This is moving downwards. Upthrust is acting. Since it is moving to downwards direction, to opposite direction, there's the resistive force or the viscous force. So it is upwards, right? It is upwards. Then we can apply F equals ma to this case and we can describe the motion of this. You have to clearly understand, this is a bit complicated, you have to clearly understand at each step what happens here, right? Under that topic you wrote, put simple A, don't draw this yet, just put simple A. In front of simple A, write moment of release. Moment of release. Write that down. Don't draw this. Write moment of release. Under that, write at the moment of release, comma. So when you release an object, what happens? When you release that, initial velocity is 0, right? Understood? V equals 0. The moment of release, let's say you here, and you just release that. Initial velocity is 0. Okay. So if initial velocity is 0, what is the force? Viscous force also should be 0. Why? See this term here? If V is 0, F is 0, right? So at the releasing moment, once you release that, initial velocity is 0. So is viscous force. Just write this down. V equals 0. Therefore, F equals 0. Then below that write, therefore, acceleration. Acceleration is maximum. Write that down below this. Acceleration is maximum. So initially the acceleration is maximum, right? Okay. So according to this one, at the initial moment, this F is 0, right? This F is 0. I'll just write with the F. Now I'm going to apply. So let's say this accelerates downwards. I'm going to apply F equals ma downwards to this ball. So what are the terms? mg downwards minus F minus u equals ma. When the object moves downwards, do you understand? mg and u, these are constants, right? Weight of the object does not change. When it moves downwards, weight of the object does not change. Upthrust also does not change. Upthrust is V rho g, right? It doesn't change, right? V means displaced volume. It doesn't change. Rho doesn't change. G doesn't change. So mg and u does not change as it is sinking downwards. But what happens with time? With time, so this is gaining some velocity. So as it sinks, this viscous force increases. Why? Velocity increases, viscous force increases. So this is a constant. This is increasing, right? F is increasing. Then what happens? Initially this is 0, but this gradually builds up. As the speed increases, resistive force also increases. So this increases. Then what happens to the net force that is accelerating this downwards? This is a constant. Let's say this value is 100 Newton. This value, when you simplify this is 100 Newton. But this F is increasing. What happens to the total value? Total value is decreasing, right? This whole thing is decreasing. So is acceleration. So this has a maximum acceleration in the beginning. In the beginning, this has a maximum acceleration. Okay? Right. So in the beginning, we don't have a F. So I'm going to remove F, right? In the beginning, only mg and u are the forces. And this has a density rho. The object has a density rho. Liquid has a density rho naught. mg, u, those are the only forces. So to this case, I am going to apply this. So this is initial moment, right? This is torque under initial moment only. At the next moment, this changes, right? Here we have the maximum acceleration because there is no resistive force initially. As the time goes, resistive force increases. So when the resistive force increases, this is slowing down, right? Not slowing down. Acceleration is decreasing. If you have a problem, let me know, right? So let's apply this. This is for the initial moment, right? F equals ma. What do we get? mg minus u equals ma. We get that. Actually, this is maximum acceleration here. Then m means what? So you know, density, this m is mass of the object. So how can we write that in terms of density? Density of the object is rho. Just multiply that by volume of the object. Let's say volume is V, right? Capital V. So rho V is equal to mass of the object. If you don't understand something, let me know, right? So mass of the object is rho capital V. Then G. Minus upthrust is what? Remember? V rho G. Same V, right? Same volume. But the density means when it comes to upthrust, density should be density of the liquid, not the object. So this is rho naught G equals, here as well you can apply rho V for mass. Right. Then this V cancels off. You can divide by V. So I'm going to derive an expression for A max, maximum acceleration. You get rho minus rho naught divided by rho times G. So this is an expression for maximum acceleration. Again, I'll tell you this is only at start. At start means when t equals 0, right? It is better to write t equals 0. At the initial moment, only you have the maximum acceleration. But after that, acceleration starts to drop. We'll see that. First, this is the expression for maximum acceleration. You don't have to remember this, right? If you get a question from this, just you have to derive this quickly. You only have to remember this equation. You don't have to derive this, right? Just remember, this is only for the start, at the initial case. Okay, take everything down. Thumbs up once you've taken it down. First draw the image, right? Then take everything down. Thumbs up, right, if you've taken it down. Amani, okay? Right. Then write simple B. So this is the initial moment. Then write simple B. That is the second case, right? Write down after a while from releasing. After a while from releasing. Okay. Now what happens? So now it's been a while, right? Not the initial moment. So this gains a velocity. Now this has a velocity. If it has the velocity, also there is going to be a viscous force acting on to the opposite direction. This is simple V. Let's say it gained a velocity v. mg downwards, upthrust. Draw this one. Just draw this. Okay, below that, right? Below that, since the sphere has a speed now, write down, since the sphere has a speed now, it has viscous force acting to the opposite direction. Viscous force acting to the opposite direction. Full stop. Same line. Therefore, acceleration is less than a max. Acceleration is less than a max. Okay. So if they ask acceleration, in this case, after a while, again you just have to apply F equals ma, right? Let's say downwards. So mg downwards, u upwards, F upwards. Instead of F, I'll put 6 pi a eta v equals mass acceleration dash. So if it is after a while, you have to apply this equation. Then depending on the question, you just have to do substitutions and all those things and get the necessary answer, right? You just have to apply F equals ma. Okay, right. Take this down. Right. Right. So this is, you have to understand now, this is having an initially a max, right? Initially a max when velocity is 0, but it gains some velocity. Now acceleration is less because there's a force acting to the opposite direction. Acceleration is less. It doesn't mean velocity decreasing, right? Even though the acceleration is decreasing, still it is an acceleration. Acceleration is decreasing, value of acceleration is decreasing, but it doesn't mean object's velocity decreases. Even though it is acceleration drops, still it is acceleration, right? So velocity keeps increasing, but the acceleration decreases. Okay, right. So these two cases we talked about, right? Initially a max, then you get a dash, then write simple c. Write down simple c, write down after a sufficient time of release. After a sufficient time of release. After a sufficient time of release. Okay. First, just take this down, then I'll explain. Quickly, we'll take this down, right? There are some notes. There are questions also I have to discuss. So, write down below that when simple v increases, when simple v increases, viscous force, capital F, viscous force, capital F, also increases after, next sentence, after F plus U equals mg, F plus U equals mg, comma, the sphere falls at constant velocity. Sphere falls at constant velocity. Next sentence. This max velocity gained by the sphere is called terminal velocity. Terminal velocity. Within brackets, V naught is called terminal velocity V naught. So this is the equation, right? A eta V equals MA. Initially, at the start, this value was 0. So we had a maximum acceleration. But as this gains speed, this term increases. 6 pi A eta V increases. This is a constant, right? When this increases, what happens? Whole thing decreases. So the right side of the equation also should decrease, meaning acceleration decreases gradually with time. Starting from the maximum acceleration, then acceleration decreases with time. And what? It keeps decreasing, right? Acceleration keeps decreasing. And it comes to a certain value, where the velocity is terminal velocity. V naught, terminal velocity. At this value, what happens? Let's say this is 100. This also becomes 100. So this V naught is increasing, right? Gradually V naught is increasing. Acceleration is decreasing. There's a certain value of V, we call V naught. At that value, this whole value is matched with mg minus u value. What happens then? This one cancels off. And the net force becomes 0. 0 equals ma. Then what happens? Acceleration is 0 at that moment. Once it gains 0 acceleration, after that, the object starts to move at constant velocity downwards. That constant velocity is what we call terminal velocity, V naught. Right? Then, so at the V naught, what happens? Now the acceleration is 0, right? At this case, acceleration is 0. Velocity is V naught. In that case, so what are the forces? Mg is downwards, upthrust. Then there's F. If you think about F equals ma now, so what are the forces? F plus u minus mg equals 0, right? Because acceleration is 0 now. You can write F plus u equals mg. F plus u equals mg. Now this is in equilibrium. This is moving at constant velocity. Okay. Take this down. Take everything down. So here I am going to prove an equation for V naught, terminal velocity. Take it down and thumbs up then. Right. Then I'm going to get an expression for V naught, right? So F 6 pi A eta. Now it is V naught, okay? V equals V naught, terminal velocity, plus upthrust. Upthrust means V rho G. So what is the volume of a sphere? 3/4, no, 4/3, 5 A cube. This is the volume of a sphere, right? V. Then rho. Rho means density of the liquid. We took it as rho naught, right? Density of the object is rho G equals now mass of the sphere. You can also find that using 3/4, 5. So this is also V rho, right? 3/4, 5 A cube. Rho means now density of the object. Rho. So that is mass times G. Right? Did you understand this equation? Thumbs up, right? Okay. Then I need an equation for V naught. You have to subject V naught. So V naught is this one, 2a squared. You have to do this simplification, right? I'm just directly writing the equation. 2a squared G rho minus rho naught divided by 9 eta. This equation you must remember. This is a large equation, but you must remember this equation for terminal velocity. What is that? 2a squared G rho minus rho naught divided by 9 eta. You have to remember this, right? Okay, take it down. I just directly wrote the equation, right? You have to simplify, then take the equation, right? Once you are done, thumbs up. Check whether this is correct, right? Thumbs up if you are done, right? You have to get 2a squared G rho minus rho naught divided by 9 eta. Did you get that? Thumbs up if you are done. Right. So this is what happens to a small sphere falling through a liquid, right? I'll just again revise you that. Initially, since the velocity is, it has maximum acceleration downwards. Velocity is 0, right? But as it falls through, it gains velocity. So as it gains velocity, velocity increases because it is accelerating downwards, right? Velocity is increasing. When velocity increases, what happens? F also increases. Resistive force also increases. Because this increases, now the acceleration is decreasing. Because this is resisting the motion, right? So the acceleration is decreasing. acceleration is decreasing, but it does not mean that velocity decreases. Even though acceleration decreases, it is still acceleration, right? So velocity keeps increasing. There's a certain velocity V naught, terminal velocity V naught. When it comes to V naught, what happens? This F is sufficient enough to stop the acceleration, not the motion, right? Stop the acceleration. Now the acceleration becomes zero, right? Now the object is balances out. mguf balances out. Now the acceleration is zero. At that moment, the velocity gained is called V naught, terminal velocity. Then what happens? The object keeps falling at terminal velocity, right? So this is what happens to raindrops, right? You know, a raindrop starts from like I think 1.5 kilometers, right? From a cloud. Just think about the speed it achieves as it reaches the ground, right? If you just apply 10 meters per square second, that speed is going to be like very huge, right? That speed is very huge. It gains like a speed like a bullet, right? But that doesn't happen, right? Raindrop just has a usual speed, right? It has a normal speed. Yeah, maximum velocity, yeah. You can think that way as well. It gains maximum velocity. After that, velocity does not increase. Okay. Initially, the velocity is zero. After that, it reaches terminal velocity. Then it does not increase. So what happens to a raindrop? It starts, then it keeps accelerating. After a short while, the forces balances out by the resistive force acting on the raindrop. Once it is gained that velocity, then what happens? It reaches the ground at constant velocity. So that raindrops has a constant velocity. Initially it is accelerating, right? Initially accelerating, then acceleration stops. After that, it keeps a constant velocity, right? A raindrop, when it falls like, let's say 100 meters, once it falls 100 meter from the cloud, right, it gains its terminal velocity. After that, it drops to the ground at constant velocity, which we call terminal velocity. So that happens to anything moving in a medium, right? Moving in a resistive force. Once the resistive force is sufficient enough to stop the acceleration, then the object has a terminal velocity. So you have to understand that, right? So, but here we are only talking about a small sphere, right? For different objects, we have different equations for F. This is only can be applied for a small sphere. For others, you cannot apply that, right? I gave you the assumptions when I'm discussing Stokes equation, right? So you have to follow those assumptions, only apply. So this is the only equation in the syllabus, but for different shapes, you will have different equations. So those are not in the syllabus. If you have a different shape, they give you the equation, right? But this equation you have to remember. Right, there are some points you have to take down. First point, put asterisk mark, write down. Quickly we'll take this down, right? Write down when radius of sphere is larger, when radius of sphere is larger, terminal velocity is larger. or higher, right? Terminal velocity is higher or larger, whatever. So how do we know that? If we have a solid sphere, this should be solid, right? Solid sphere with a larger radius. Larger radius. So how do you get that? You get that from this equation. Terminal velocity is proportional to radius squared. So makes sense, right? If radius is higher, terminal velocity is higher. Write this below that sentence. Then another sentence. When another sentence means another point, right? Another point. When two spheres with same radii means multiple radius, right? When two spheres with same radii but with different masses are released in a liquid V naught of sphere with higher mass V naught of sphere with higher mass is higher. V naught of sphere with higher mass is higher. Within brackets, right? The reason for that, right? Within brackets, right? Since upthrust is same, to balance a higher mass, a higher viscous force is required. A higher viscous force is required. Close brackets. Done? Right. So at the terminal velocity, this is the equation, right? mg and u, no, other way, right? mg is equal to u plus f. Weight is balanced by u and f. U and f is upwards, right? Weight is downwards. So the object is in equilibrium. It is moving at constant velocity. So what does this say? Upthrust does not change, right? It is a constant. Understood? When you compare two spheres, two solid spheres, that's what it says in the question, right? I mean expression. You have the same radius, right? If you have same radius, but the masses are different. Let's say mass here is m1, mass here is m2. Let's say m2 is higher than m1. How can this happen? if the density of this one is higher, even though this has the same volume, same radius means both have the same volume. If density of this one is higher, this has a higher mass, right? Higher density, higher mass. We know that upthrust is constant. It doesn't change, right? Because volume does not change. Volume is the same for both. So upthrust is same for both. Then if mass increases, what happens? Force increases. Force means viscous force. So you need a, this has 6 pi a eta v naught. Higher means v naught is higher. Understood? So if you have a higher mass, when you're comparing two spheres with same volume, right? If you have a higher mass, you have a higher terminal velocity, right? You don't have to remember these precisely, right? As it is. When you get a question, you quickly, you quickly have to derive some form of this, right? Derive and get the answer. But that equation, you must remember, right? Those which we drew margins, those equations you must remember. These facts, you just have to know these, right? You don't have to remember. You quickly have to derive and get the answer, right? If you can remember, it's better, but it is not necessary. Below that, right? It spends more time to reach V naught as well. It spends more time to reach V naught as well. It spends more time to reach V naught as well. So this has a higher mass. V naught is larger, right? For this one, V naught is larger. If it has a larger terminal velocity, this takes some time to gain V naught, right? The time taken also is higher for this higher mass. Okay? You need to have a rough, not understanding. You need to have a clear understanding, but rough memory of these, right? Then you can quickly derive this and get the answer. Okay, put the next asterisk mark. Write down. Consider two spheres with same mass and same radius. Same mass and same radius. Same mass and same radius. Full stop. One is solid. Other one is hollow. One is solid, other one is hollow. Full stop. Since they are mg and upthrust U, capital U, are same, are same, if also, if also there should be if not, right? If not, if not also is the same. If not also is the same. Therefore, therefore, both spheres have, both spheres have the same V naught, have the same V naught. Done? Everything taken down, right? Right. Now I'll explain this. You have a solid sphere, you have a hollow sphere. Falling down, right? We are only talking about terminal velocity, right? Not before that, at the terminal velocity and after. So both have the same mass and the same volume as well. If they have the same mass, both have the same mg, right? If they have the same volume, upthrust also is same. Volume means upthrust means V rho g. V rho g is also same for both. So what's the equation? Mg equals U plus F. If both, when you compare these two, they have the same weight and the same upthrust. So for both, they should have the same F as well, right? You should have the same, F means F naught actually. F naught means viscous force at terminal velocity. Both should have the same F naught. If both have the same F naught, V naught also is the same. It doesn't matter one is hollow, right? If they have the same mass and same volume, it does not matter that V naught also is same. It does not matter one is hollow. Understood? Put the another asterisk mark. Write down if density of okay, okay, here this is solid, this one is hollow, right? Both have the same mass and same volume and same mass, both. Okay, so this is the equation we apply. Mg equals U plus F naught when it comes to the terminal velocity. So both have the same weight and the same upthrust. If they have same, when you compare these two, F naught also should be same, right? Because if these two are the same, this also should be same when you compare these two. If F naught is same, you know this is 6 pi A eta V naught. V naught also should be same. This cannot have a different V naught. It doesn't matter one is hollow, right? It doesn't matter one is hollow. You need to have a kind of like a rough memory of this, right? Rough memory of this. Then you can if you are not sure when you are doing the exam, right? When you're doing the exam, if you are not clearly remember, then you can quickly derive this and get the answer, right? One is solid, other one is hollow. but both has same mass and same volume. So even though one is hollow, it does not matter. Both will have the same terminal velocity, right? Right. Then put the another asterisk mark, write down if density of solid sphere, if density of solid sphere is less than density of liquid, if density of solid sphere is less than density of liquid, comma, when the sphere is released, from bottom of the liquid, comma, as it moves up, viscous force, capital F, viscous force, capital F, develops, then reaches terminal velocity, V naught, terminal velocity V naught. Right? Okay. Done, right? Okay. So for these ones, I only talked about objects moving downwards, right? Sinking. Then what happens if you have an object, let's say like plastic object in water. So what happens when you release the object from the bottom? It goes up, right? So when it goes up as well, same thing happens, right? So let's say this is water. So this goes up. Upthrust is upwards, mg. Now the upthrust is higher. This tends to move upwards. Then if it is moving upwards, now the friction force, viscous force is downwards now, right? It always opposes the motion. It is downwards now. So at the initial moment, what's the acceleration? Initially, V is 0. You are just released that, right? Here you release that. V is 0. So F also is 0. Then you need to find acceleration. Let's say maximum acceleration. U minus mg. U upwards mg. You apply F equals ma upwards. U minus mg equals m a max. So this U, you can write it as V rho naught G. This you can write as V rho G equals V rho G A max. So when you get rid of V, what do you get? Rho naught minus rho divided by rho. So this is A max. This is similar to the previous case, right? Only thing is you just apply the equation upwards. Do you understand that this term gets switched? So you can check the previous A max equation, right? Maximum acceleration equation. What do you get? Rho minus rho naught divided by rho g. Now here rho naught is large, right? Because it is going upwards. Now you just have to switch this one, right? Okay, just take this down. So this is when you get a problem when the object goes up. So all the other equations also can be derived, right? You don't have to remember each equation. You can derive these. And the equation for terminal velocity change like this. Just take this down as well, 9 eta. All that happens is this changes, right? Rho and rho naught switches positions. Because for these, rho naught is larger than the density of the object. Take both down. Right. Then we have to go for graphs, right? If you get an object falling through a liquid, you need to get graphs. First, I'll draw velocity time graph. It is somewhat easy, right? Now listen carefully. So the object is falling down, right? So initially, when time is 0, in a velocity time graph, what's the gradient? Gradient is the acceleration. I think you know, right? Gradient is acceleration. So at the initial moment, it has the maximum acceleration, meaning maximum gradient. So initially maximum gradient, right? Meaning maximum slope. As it falls down, what happens? Acceleration drops, meaning the slope is decreasing. So this should be curved. Understood? Slope is decreasing, right? Slope is decreasing. Then this decreases up to 0. Acceleration becomes 0 then. At this moment, it has gained terminal velocity. So the slope also is 0, meaning at this point it is flat. At this instant, slope gradually decreases and becomes 0. Gradient, right? So let's say that time is here. After that, what happens? So this happens at terminal velocity. After that, it keeps moving at terminal velocity. Now it does not have an acceleration, it is just have a constant velocity. So velocity is constant. This is velocity time graph. Do you have any problem regarding this? If not, thumbs up, right? Okay, I'll explain again, right? So because this is very important. So in a VT graph, all you have to know is gradient of a VT graph is acceleration, right? Gradient of a VT graph gives us the acceleration, right? Gradient equals acceleration, or in simpler terms, you can think about slope. Okay, slope means like this. If it is like this, slope is higher. Slope lowers, right? Slope decreases. Slope increases. When slope increases, gradient also increases. Initially, this has the maximum acceleration. Maximum acceleration means maximum slope or maximum gradient. Here, do you see that? Just draw a tangent to this point. Or you can place the ruler to this point, right? When you draw a tangent, imagine a tangent, it has the maximum gradient, right? Then as you go along this path, what happens to the gradient? It is decreasing. See there? It is decreasing. So gradient is decreasing. What does it mean? Acceleration is decreasing. This is what happens, right? Starting from maximum acceleration, it decreases. Then acceleration decreases, then becomes 0. When it is 0, gradient is 0 at this point. Then it gains the V0, that is the terminal velocity. Once it gains terminal velocity, then it keeps moving at terminal velocity. Understood? All right, okay. Okay. So now we draw VT graph. Okay. So this is very important. Then you need to draw ST graph. So it is somewhat complicated to think about acceleration using a ST graph, right? So based on this, I'll convert this into a ST graph. Right. So here what has happened? Velocity increases, right? Then becomes a constant. We cannot clearly show the acceleration increasing, right? In a ST graph. But we can only show the velocity there. So in a ST graph, velocity means gradient. Here velocity is gradient. Now do you see that velocity is increasing, right? So if velocity increases, gradient increases. Gradient increases means like this. Remember the slope? Slope is increasing. See that? Slope is increasing. Then what happens to the slope? Slope becomes constant. Not 0, right? It is a constant. Like this. So this is a straight line. Here it is curved. So this is a ST graph. Then I'll draw AT graph, acceleration time. So what happens to the acceleration? When time is 0, acceleration is maximum. Here acceleration is maximum, right? When time is 0, maximum acceleration. But with time, what happens? Acceleration decreases and becomes 0 as it gains the terminal voltage. So terminal velocity. Acceleration decreases, then becomes 0. After that, acceleration is 0. Right? So these are the ST, VT and AT graphs. You have to again revise these, recall these, right? Again, you have to draw these. Then you would have the perfect understanding, right? Right? You don't have to draw these, only take, not these, only take down these 3 graphs, put asterisk mark. In front of the graph, I need to write some sentences, right? So leave some space in front of each graph. Quickly take it down. In front of each, I need to leave some space, right? Right. You have to revise this again, right? This again. Right. In front of ST graph, write this down. Since V increases, gradient increases. V increases, gradient increases. Full stop. Same line. After reaching V naught, gradient becomes constant. Gradient becomes constant. Okay, so that is in front of ST. Then in front of VT graph, write this down. Since acceleration decreases, gradient decreases. Since acceleration decreases, gradient decreases. After reaching V naught, graph gets horizontal. Graph gets horizontal. Okay. Then in front of AT graph, write down. At initial moment, simple A is maximum. Then acceleration decreases and become zero. Acceleration decreases and becomes zero. Right, okay. These now the theory part is over, but these These important points are based on the questions, right? You might get. So you have to pay attention to these as well. These are based on questions, okay? Okay, and then put next asterisk mark. Uh, if the sphere is released from simple h height from the liquid surface let's say everyone connected, right? No connection issues, okay? Amani? Okay. I write down, let's say velocity is simple v. Velocity is simple v. Okay. So this is another type of questions, right? Another types of questions. So this is the liquid surface. You release an object not within the liquid. So previously when we are discussing the theory, the object is, as it released, object is inside the liquid, right? Or at the surface. But here object is above that. So you have to know what should you do in a case like this. So what should you do? Now the object is released from a h height. So as it reaches here, by applying motion equations or energy equations, you can say as it reaches to the liquid surface, it is 2gh root. Okay, I think you know that. V equals 2gh root. You just apply v squared u squared to as. So you can get 2gh root as it reaches the liquid surface. So this also has three cases, right? Let's say this v is equal to v naught. So initially zero velocity, but this hits the liquid surface at terminal velocity. So previously, right? Previously, object is released. So it had zero velocity. And it just released and gained terminal velocity somewhere here. But here what has happened? As it enters the liquid, already it has the terminal velocity. So it is simple A case. Then we can think about simple B. Another scenario. If V is less than V naught, this V could be less than V naught, less than terminal velocity. Somehow at the end, everything has to gain the terminal velocity, right? Here it is already gained. Here it is not gained. What is the another scenario? This velocity could be greater than terminal velocity. This is another scenario, or the another way you get questions. Could be the velocity that the sphere enters the liquid is greater than terminal velocity. So that is another scenario. So here we have to draw some graphs, right? So under this case, what could happen? I'll draw VT graphs. I'm drawing the graph from here to here, right? From the start. So t equals 0 is here. So it just drops at g, constant acceleration, right? Before entering the liquid, it just drops at 10 meters per square second. So it is a VT graph, slope is a constant. Then after that, it enters the liquid. Because this already has V naught, what happens now? Nothing happens. It just moves at V naught because it already has V naught. It doesn't have to decelerate, right? It doesn't have to decrease its acceleration in order to get V naught. This already has V naught. It just dropped through the air at G. Then as it enters the liquid, it already has terminal velocity. So it doesn't have to accelerate in order to gain. So it just keeps moving at V naught. And at the end, all it needs is what? To gain the terminal velocity. This already has terminal velocity. So it just keeps moving at that through the liquid. Then the second case, right? Now this doesn't have terminal velocity. It hits the surface but at a low velocity. So what happens? Here it just drops. It just drops through air. Then enters the liquid. But in this case, this has to accelerate, right? This has to accelerate in order to gain the terminal velocity. In order to gain the terminal velocity. Let's say this is terminal velocity. It needs to gain the terminal velocity. But acceleration decreases, right? Then gains the terminal velocity. So here acceleration decreasing in this part. In this part acceleration is g. In this part constant velocity. Get it? At the end, anyway, it gained the terminal velocity. Right? Then at C. So as usual, it just drops through air. Constant gradient. Drops through air. Constant gradient, right? Gravitational acceleration. And as it hits the liquid surface, it has a velocity which is greater than terminal velocity. This velocity is greater than terminal velocity. Terminal velocity is less. It is a value somewhere here. Now what happens? Inside the liquid, now it has to decelerate. It decelerates and then at the end it gains the terminal velocity. So this is the graph in a case like this. At the end, everything has to gain the terminal velocity. if it is terminal velocity, it keeps having the terminal velocity through the liquid. If it doesn't have terminal velocity, it accelerates and gains the terminal velocity. If it has more than terminal velocity, it decelerates and gains the terminal velocity at the end. Okay, so these are, you will need these in the, when you're doing questions. Okay, okay, quickly take everything down. If you have problem, let me know, right? You have to revise this again. Okay, there's a one more theory part, right? Write down the topic, simple experiment, then we are done, right? Write down simple experiment to compare viscous coefficient to compare viscous coefficient eta. So this is like a, it is a, not like, it is an experiment, but not a standard one, but this is for the comprehension, right? First, quickly take this down. Write down below, a tall beaker is filled with the first liquid, and make sure the liquid height is enough to reach V naught. Liquid height is enough to reach V naught. Then measure the time required for the sphere to fall within a certain distance within brackets simple L, certain distance simple L. Okay, separately write replace the first liquid with second liquid then measure T2 means simple T sub 2 in the previous sentence there's measure the time required, so for that, right, T1, right, that time is T1. Okay, right. So this is what you do. Listen carefully. Okay, you just get a tall beaker, right? Then you fill the beaker with a liquid. You fill the beaker with a liquid. Then what do? You release a small sphere. Let's say like a iron sphere, small one, right? You release it here. After it falls through the liquid, let's say somewhere here, that's why you need a sufficient height of the beaker. You know, after a while it gains its terminal velocity. Let's say it gains its terminal velocity once it reaches here. If you let it enough distance to fall down, it reaches the terminal velocity. It doesn't take that much time, right, to reach the terminal velocity. It quickly gains its terminal velocity. Then it falls through L. So this is liquid 1, right? Liquid 1. Then what do? You have to observe that. You have to start the stop clock as it enters from here and leaves from here. Within this region, this object moves at V naught, right? Object moves at V naught. I'll say V1 because it is first case. Terminal velocity as the first case is V1 because within this region it has a constant velocity. Okay, so for constant velocity, you can apply S equals ut. Let's apply that. L equals V1 time you have to measure, right? T1 is the time. So for this one, L equals V1 T1. Got it? Then V1 is equal L divided by T1. Also V1 is equal to what? Terminal velocity. What is the equation for terminal velocity? You must remember this. UA is 2A squared G sigma minus rho divided by 9 eta. Here it is eta 1, right? For the first liquid, viscous coefficient eta 1. Let's take like that. Eta 1. And the density of the liquid, I'll take it as rho 1. This is density of the liquid, right? Rho 1. This is density of the sphere. We are not changing the sphere. Okay, we took V1. Then what do? You empty the cylinder, beaker. Then you put another liquid. Let's say oil, some type of oil, to the same height. And you measure this, you keep this level to the same. Only the liquid is changed, right? So for the next liquid, terminal velocity obviously different, right? So it is V2. Length does not change. Now it takes a different time because terminal velocity is different. Length is the same. These are the marked lengths, right? So V2 is equal to what? A squared G sigma minus, now the density of liquid changed. Radius does not change, right? Same sphere, we are using the same sphere, solid sphere. Divided by 9, different coefficient. Then what do? Let's say this is first one, second equation. Just divide first one by second. L cancels off. When you divide this becomes T2 over T1. This flips, right? Equals, these cancels off. 9 cancels off. So what do you get? Eta 2, everything flips, divided by eta 1. Eta 2, you get sigma minus rho 1, right? Divided by sigma minus rho 2. You can do these calculations again, right? And then find that out. So here we have to then cross multiply. You get, what we need is to compare these two viscosities, eta 1 and eta 2. Then cross multiply. T2 goes to the other side. T1 sigma minus rho 2 divided by sigma minus rho 1. Right? Using the stopwatch, you can measure these T1 and T2. And sigma is known, right? Sigma is the density of that sphere, object. Those are known spheres. Then densities of liquids also, you have to know that. So everything is known, then you get a value here. Let's say 1 over 2 or something. Then what can you do? You can say, viscosity of this liquid is twice the viscosity of fresh liquid. Or else, if you know the viscosity of fresh liquid, you can actually find the viscosity of second liquid. Okay, take it down. Take everything down. Thumbs up if you are done. Below that, write, since T1, T2 are measured and rho, not rho, sigma, right? Sigma, comma, rho 1, comma, rho 2, rho 1, comma, rho 2 are known, are known eta 1 and eta 2 eta 1 and eta 2 can be compared. Eta 1 and eta 2 can be compared. Eta 1 and eta 2 can be compared, right? So that is all the theories, right? All the theories now on viscosity it is done and dusted, right? Then I'll have to discuss some of the questions. We'll do that. I'll just need like a half an hour, right? Just get it done now, right? You don't have to postpone that. So get the tute. Just hold on for another half an hour, right? We'll get that done now. Okay, get the tute. Get the tute. Get it done now, right? Just hold on. Okay. Turn to the Stokes equation at the below fundamentals. At the last class, we discussed some fundamentals. Multiple choice, then fundamentals. Below that, we have Stokes equation. Page 7. Try the first one and let me know the answer. First one means 31st question. Viscous force acting on a ball with radius r, moving at v through a liquid with density d is. Yeah, third one, right? So it is just asking about the equation. Then 32, 6 pi a eta v, just the equation, right? Third one. Okay, 32. On a large liquid surface, a ball is released. Unbalanced force acting on it is. Yeah, fourth one, right? So unbalanced force. Unbalanced force, you can think that in terms of acceleration. So what happens? Acceleration decreases and it becomes zero. So the same thing happens to the unbalanced force. Fourth one, correct. 33, next one. Yeah, first one, right? Velocity. We don't have a mass term here, right? We don't have mass here. So proportional to the velocity. There's no inversely proportional. It is proportional to radius, right? Not inversely proportional. So first one is the answer. Next one, 34. 34, fifth one, yeah, is 0. 35, acceleration is 0 at terminal velocity, right? It is 35. Yeah, second one, right? So velocity increases, then reaches terminal velocity, then, yeah, second one, correct. Then it has a constant velocity, right? We'll do this next one at 36. See the same question? Oh no, it is about resultant force, right? So what happens to the resultant force? Yeah, fourth one decreases and becomes 0. That happens to the acceleration. Same thing happened to the resultant force or the unbalanced force, right? Then we'll move on to some numerical questions. Try next one, 37. Radius r, density d. eta density of liquid d naught, maximum acceleration. Or the initial acceleration. So initially there's no velocity, right? Maximum acceleration means, okay, I'll just do that. Initially we don't have a velocity, right? If we don't have a velocity, we don't have a viscous force. So this only has mg and upthrust. These are the only two we have. So in order to find the acceleration, you have to apply F equals ma. So what are the forces? Mg minus u equals ma. So let's say volume is V. Let's take the volume as V. So mg means V times density of object, right? This m means density of object, which is d, not d naught, it is d. Minus here V rho g, V density of liquid for upthrust, d naught. Don't mix that up, right? Equals this mass density of object, d, a. V cancels off, d minus d naught, take g out, divide by d. So this is the acceleration, right? We actually derived this earlier as well. You don't have to remember this, right? Only the main equations. These ones you have to quickly derive and get the answer, right? Okay, then they ask the terminal velocity, 38. Try 38. For the same scenario, they ask us terminal velocity. Get an expression for terminal velocity. 38. So at the terminal velocity, what happens? U plus F. This comes to equilibrium, right? Forces upwards equals forces downwards. So U plus F equals mg. This has radius. So it's better to use, instead of V, it's better to use this one, right? 4/3 pi r cube. Because otherwise it will be difficult to simplify, right? Because there's for F there's a r there, right? I'll give you a minute to do the substitutions. Okay, U is V rho g. 4/3 pi r cube. Rho means don't mix rho and rho naught. D, right? D naught. V rho g. 6 pi r. A means r. 6 pi a eta. V naught. Velocity is V naught. Terminal velocity. Equals 3/4 pi r cube d, density of object, and g. You need to subject V naught, which becomes the terminal velocity, which is the terminal velocity. You have to carefully do the simplification, right? Because this is somewhat complicated. We get this standard equation, right? Yeah, second one is the answer, yeah. because there's nothing is different there, right? I thought there's a difference, but we get the same, I mean, standard equation, right? I thought it will be different. No, because all the terms are same there. But for terminal velocity, depending on the question, you might get a different equation, right? Let's say the values are given in mass only. So you might get a different, you just have to get you have to remember this equation, right? Then next, Yehansa, are you okay? You get the same standard equation for terminal velocity. In some cases, you get a different equation. It depends on the question, right? I mean, in terms of R, eta, and density, you get the same equation. But let's say you got like a mass and all that. In that case, you might get a different equation there, right? Okay, then try next one, 39. You have to remember this equation. You must remember this. Yeah, it should be a fourth one. Because force is proportional to radius, right? Force is proportional to radius, viscous force. So the correct answer should be 1:2, right? Not 2:1. Just write it as 2:1, right? Next one, 40. Terminal velocity proportional, right? Proportional, directly proportional, not inversely. So V1 over V2 should be what? Just consider the standard equation, right? Remember in the standard equation, V is proportional to R squared. A squared to R squared. 40, right? Not 41. R1 and R2. I don't know why you say 104. For the first case, V1 proportional to R1 squared. Second is here, this one. You get rid of all the constants. You don't need constants, right? Maybe you are thinking about these two. You don't need both, cancels off that one. So what do you get when you divide? R1 squared divided by R2 squared. Understood? Third one, right? Not the other way around. The ratio should be in order, right? If you divide first one, second one, then other side also first one, second one. If it is inversely proportional, then second one, first one, right? Aman, did you understand that? I'll do one more question, right? Try 42. Okay, let's see. So we have n number of raindrops, small raindrops. Now listen, right? Each has 2 millimeter radius. And by collecting n number of these raindrops, what do you get? You create a larger raindrop. So you can understand when you compare these two, variables are terminal velocity and radius, right? You don't need all those. So you can think about V and A only. You don't need the whole equation. V and A squared. So this is 2 millimeters. What's the radius of large? A radius is not given. Let's say radius of the large one is simple A. This has a terminal velocity 32 meters per centimeters per second. The small one has a terminal velocity, what? 8. Right? So I'll apply this here. V is proportional to A squared. So here velocity 8 proportional to A squared, meaning 2 squared. If you apply second case, 32 is proportional to A squared. So using these two, you can find radius of this sphere. I'll just divide from this one to this one. A squared divided by 2 squared equals, 2 squared means 4, equals 32 divided by 8, that is 4. So A squared is 16, so A is what? 4 millimeters. So by collecting all these raindrops, you get a raindrop which has a radius 4 millimeters. So first you have to find the radius. Understood? Then how do you find the simple n? Simple n. In the question they ask how many raindrops did you have to collect? That you have to collect to create this. When you get a question like this, sum of volume is equal to sum of each volume of each raindrop is equal to the volume of the large raindrop. Volume, right? Or we can say mass, sum of mass. You cannot say radius. Okay? You cannot say this is 4 millimeters. Then this is going to be 2 raindrops in order to create 4 millimeter radius. You cannot say that, right? You cannot add radius. You can add volume. So let's add volume. A small raindrop. So it is 3/4 phi r is 2 millimeter cube. This is for a small raindrop times n. N number of small raindrops is equal to the volume of large raindrop. So phi, radius of the large is 4. 4 cube. 4 cube. Then using this one you can find simple n. Get rid of 3/4. N is equal to what? This is 8. 4/3 means, I'll just write it as 4 times 3. 1. Yeah. 8, right? Third down. Okay, so when you get a question like this, you just have to add the volumes, right? Not the radius or the areas. Those cannot be added, right?